Yes, hello. So yeah, let us begin. I didn't hear the beep, but I assume it happened. Maybe my laptop was on mute. Okay, so we are continuing from last time where we discussed the rank nullity theorem. So today we will talk about, there will be one other application of that, but first let me just get back to ordered bases and finish a couple of things. Okay. So remember that so if you have ordered bases again. So if you have a linear transformation between two vector spaces, let's say V and W are finite dimensional over F. Okay. And you're given two ordered bases. Ordered bases of V and W respectively. Then what you can do is you can write down every vector, first of all in terms of its coordinates, like you get coordinates. And so these lead to what? It leads to, so for all V in V and W in W, let's say of dimension M and N. So N is the dimension here and M is the dimension here. So for this you get VB, this is an F to B N, and from here you get WB dash, and this is a vector in F to the N. And then you also get a matrix. Okay, this is one thing. And then for all the V, you get V. For all W in W, you get W. And for all T, like that, you get, this is a matrix, which that's a B prime and B. Right? And this is in F to the M cross N. Okay, so these are what we got. And then we of course have this thing that we have the fact that there exists a unique matrix. Given a T, there exists a unique matrix, this thing, such that TV in B dash is the same. So whether you act on the vector and look at it in without a basis, or whether you act on the vector by a transformation and look at it in the basis, the same equation holds, which is this is B dash B times B. B is a vector here, not a B. So this is what it was. Right. So now this is how you compose a matrix and a vector on which it acts. Now what I want to do is I want to compose a matrix and two vectors. Right. So I want to compose a matrix and another matrix, or basically two linear transformations. This is what is so that's what we are going to do. So for example, so let me write the heading. Composing linear transformations. Okay. So the example I want to do, let's say the field is the real numbers, and the vector space is, both vector spaces are the plane R2, and the operations, so for all theta, let T theta be the linear transformation which rotates counterclockwise by theta. Belongs to lin BW, be the rotation, be the counterclockwise rotation. I think this was one of your homework 4 or 5 or something like that. Rotation by theta. Right, so that means that T theta of 0 is 0. And T theta of, if I identify the plane in polar coordinates, like complex numbers of polar coordinates, T theta R e power I theta, R e power I, let's call this theta 0. This is equal to, so then when R is bigger than 0, then this is equal to R e power I theta plus theta 0. Actually, I don't even need to say bigger than 0, r can be bigger or equal to 0. So this is polar coordinates equation, but the point is that you can write the matrix of this down with respect to the standard basis vectors, basis, as in your homework 4 or 5 or something. So now, okay, so you have t theta. Now what happens? So first of all, note that this does not require any basis to be stated, right? This can be stated completely precisely. So did not need a basis. Did not. I said this earlier, I think, in the earlier class. A basis to be defined. Right? You can define that. Take a vector and rotate it by counterclockwise. That does not require a basis. But now, secondly, now for all, so suppose I rotate by say 90 degrees and I again rotate by 45 degrees. Then what have I done? I have rotated by 135 degrees. Right? So what we are saying also is that these maps satisfy t theta composed. Sorry. If I rotate by so if I start with the vector v and I rotate by t theta, and then I again rotate by t theta dash, let's say, then that is the same as saying this is t theta plus theta dash of v. Right? That is obvious. So this is true for all v in v, in R2 basically, and for all theta and theta dash in the real line, for all angles. But what does that mean? Well, look at this vector, look at this transformation, right? So both sides start with the vector v and then change it in some manner, of course, in the same manner. This is, and the manner in which they change it is linear because the rotation is a linear transformation. That means whatever I'm doing here, first apply this, then apply this, is a linear map. And that map is what we call the composite, right? So this is the same as being called t theta, composed t theta, sorry, this is t theta dash composed with t theta applied to it. The definition of a composite map is that it is that the two maps applied successively, one after the other. And indeed, that turns out to be a linear map, which is equal to this. Okay? And the point is, this happens in complete generality. If you take two linear maps and you apply them to vectors, then what you get as a composite is also linear. And this is not just true if your v and w are the same vector space. It is true as long as the composite is defined. So let us take a look. Okay, so definition, I guess. Well, it is proposition, fine. So okay, so definition first. Given vector spaces, v w x over f and linear maps that's it. I think it's t from v to w and s from w to x. Define the composite to be the composite function, right? You can compose two functions and that's all we are. The composite function. They are composite. Or their composition, I think. Okay. Now proposition with the above notation in the above setting, in this setting. So I just know that S composed T is the composite of these two functions. Yes, sure, these two functions are linear, but that does not automatically, that does not obviously automatically imply that S composed is linear, but we can indeed say that. S composed is linear, and let's say, so first of all, S composed T is indeed a linear map from V to X. But secondly, now suppose I also add ordered bases, say V, W, X are, I did not say finite dimensional, so now I will. Finite dimensional. So are all finite dimensional over F. Let's just say finite dimensional, we know that they are over F, with ordered bases B, B prime, B double prime, okay, respectively. Then what can you say? Fine. Then you can say, now I can write down, oh, I erased it, sorry. I can write down the matrix of S, the matrix of T, and the matrix of S composed T. Right? And we saw how we talked about vectors, T, V. The vector of TV is the matrix of T times the vector of V. Well, if you think about it, vectors are a special case of matrices. Right? Scalars are a special case of vectors, vectors are a special case of matrices. So that equation that I wrote down is going to be generalized. That's all that it's the same. If one of these vector spaces is one dimensional, then you get vectors, but in general, it's a matrix. So then, if you look at S composed T, this goes from V to X. So therefore, I can look at that in the basis of X and then V. On the other hand, obviously, you can imagine what I'm going to write here. I can write down the basis of S in terms of S goes from V to W to X. So this is B double prime and then B prime. And I can write down T. This is B prime and B. And these are now, all these three of them are now matrices. Actual matrices of scalars in F, right? They are no longer linear transformations, they are matrices. And guess what? Indeed, this matrix is the product of those two. That is literally the theorem or the proposition. It's not really a theorem. It's very straightforward, obviously. There's nothing subtle or deep in this. It's all very expected, but yeah, let's write down the proof then nonetheless. Okay, so proof. I think this was everything in the theorem. Well, okay, so let me just make a remark. In particular, let's look at the right-hand side of this equation. Clearly depends on the B prime, and you're writing down the matrices with respect to the basis B prime. But on the left-hand side, there is no B prime, so this does not depend on B prime. So in particular, the right-hand side does not depend on B prime. So it seemingly looks as if it does. Right? The word B prime occurs there. But it's like saying, that if you have 5 divided by 5 or x divided by x times y, then that does not depend on x as long as x is non-zero. So something like that. As long as B prime is a basis, it doesn't depend on B prime. So that's what this is saying. Okay, proof. I think that's it. So proof. Oops. So let's just do this step by step. So the first one is that it's linear. So how do you check it's linear? You look at both sides. Sorry. You evaluate this at C times D plus V prime. Right? So S composed T at CV plus V prime. C is a scalar, V and V prime are vectors, and you do the usual trick. So this is S of T of. So by definition, the S composed T means S of T of CV plus V prime. But now T is linear, therefore this is S of C times T of V plus T of V prime. But now S is linear, so S of scalar times something plus something else is exactly, so this is T is linear. I won't even write this down, and neither should you at this point. Okay, this is S of T of V, and then the scalar goes outside, plus S of T of V prime. Right? But now S of T is the same as S composed T, so now we are done. That's why it's linear. Second, the second is similar, I guess. What do you want to show this thing? So, this is where we again use the homework problem, right? So, homework problem or something like that. I forget which homework. Two matrices are equal if and only if when you multiply by any vector, you get the same answer. So well, you have two matrices, one on the left, one on the right. Take any vector in F to the n. So the point is this: it's enough to show that when you multiply by every vector in F to the n, but there is an isomorphism, a bijective isomorphism between vectors in F to the n and coordinate vectors of V in V. Right? So it's enough to show that that the left-hand side, when you multiply by the vector of V in the coordinate vector of V in the basis B, is equal to the right-hand side times the coordinate vector of V in the basis B for all V in V. Because there is a isomorphism, bijective isomorphism between such vectors and elements of F to the n, a linear isomorphism. Therefore, it's enough to show this thing because then this would cover LHS times every vector in Fn equals RHS times the same vector in Fn. Therefore, those two matrices are equal. Okay, but now why is this true? So well, but by an earlier theorem, by class, we showed that I just told you, right? If you have T, the matrix of T times the matrix of V, that equals the matrix of TV. So you just keep doing this. So by class, this is the right hand side times V. Now this is the product of two matrices times a vector, but because matrix multiplication is associative, this is the same as saying that this is B double dash B dash times TV in B dash. That is the associativity property, as well as the result from class. Because I'm jumping two steps here in some sense or whatever. Jumping one step. And now again, this is a vector, this is a matrix, therefore this is S of T of V. This is T of V, right? That's the whole point. But now what is S of T of V? Again, by associativity of matrix multiplication, this is S composed, or by definition, S composed T of V. But now you can again convert it back. So now you go reverse way in this direction. S composed T with respect to B double prime is S composed T, the linear map. This is where you use part 1. This map is linear. So linear map times the vector is the matrix of the linear map. And now the matrix is with respect to B double prime and B, because this is S composed T times the vector in B. But that is exactly, this is the left hand side, so you get left hand side times the V. And that is exactly what we wanted to prove. Right? We want to prove left hand side times V is equal to right hand side times V. We have done that, and therefore the theorem is true. Okay, great. So that's the end of the theorem. Okay, great. Okay, that is that proposition. Fine. Okay, the last thing I want to say about with ordered bases is about matrices of so we know that for every linear transformation you get a matrix, and then they behave very well with respect to first of all applying it to vectors, but also with respect to composing. Now, here is one question. What is the matrix of the identity transformation with respect to a basis and itself? If you think about it for a minute, that means if you take the basis to be V1, V2, Vn, and you take the identity map, it takes V1 to V1, which is 1 times V1 plus 0 times V2 plus 0 times Vn. V2 would go to 0 times V1 plus 1 times V2 and so on. So the matrix of the identity map with respect to any basis and itself would be the identity matrix. So there's not much to say about that, but I can just tell you. Remark. so given, let's say, given a vector space, given V finite dimensional, we know that the identity transformation is of course a linear map from V to V. And now with respect to then for any order basis, V equals V1, Vn of V. We have the matrix of the identity transformation with respect to the same V. V and V is the identity map. And you can in fact check that the converse is true as well. There is no other. So if there is any transformation with respect to which the matrix is the identity, then the transformation is the identity. Okay. Anyway, so the point is, first of all, this is true, right? So now you have so now this operation of assigning a matrix to every linear transformation after having fixed a pair of bases, I guess, is very nice. It behaves well with respect to composing, and it also has the identity going to the identity matrix. So what happens if my linear transformation is invertible? Well, you can pretty much guess what happens, right? If the transformation is invertible, it has an inverse which is linear. That's one of your homework exercises. So when you compose that, so what about the matrices of these two, right? So if you compose T and T inverse, you get the identity, the matrix of which is the identity. On the other hand, the composing of these two matrices is the same as multiplying the two matrices, right? So you have the composite of T inverse and T is the product of the matrix of T inverse and the matrix of T, and that product must equal the matrix of identity, which is identity. Therefore, these two matrices themselves of T inverse and T must be inverse to each other. In particular, if you have a map that is invertible, its matrix is invertible. And that's the next result. So the next result basically says, so the next I'll call it a theorem. Let's say V is irreducible. Okay, so say B and B prime are ordered bases of V over F with the dimension of V, meaning the size of both of these, equals n. Okay. Suppose I have two ordered bases, each obviously of size n, of a vector space over F, V. Okay. And let's say T is a full stop. Let T give lin be B. Okay, so T is a map from lin. So I think there are three statements. Wow. There exists a unique matrix. So there exists a unique matrix P, which is n by n with entries in F, such that if you look at the coordinates of V in, I guess, this basis, no, the other way, I don't care why. Anyway, fine. So for every vector, I write the vector in terms of these two bases. There is a unique matrix that relates the two sets of vectors. Okay, great. The second is, okay, I think, let me just put it the way I have done it here. The second is that you can say something about so this matrix will relate every linear transformation with respect to this basis and that basis. T, B prime, I guess, is P inverse, the matrix of T. This is a matrix, remember? So everything here is a linear algebra, no? So P inverse times T times T. For all T. and third. And the third is the thing that I sort of said. This T is invertible if and only if the basis of T in this basis is. So T is invertible. I'll just say invertible and skip the is. If and only if the map of T with respect to any basis. I'll say I'll just use whatever here. I chose these bases arbitrarily. I didn't have any. So you take any basis and any basis B dash. And if with respect to those two bases, the matrix is invertible, then T is invertible. That is the theorem. Okay, let's prove the theorem. Okay, oops, sorry. So what do I want to prove first? Okay, the third one is a long one. So first let's start with one. So we already proved this theorem that given any linear transformation, there is a unique matrix such that T times whatever TV vector equals that matrix times the V vector. But this is exactly what this says. Consider the identity matrix, identity transformation. Apply a previous result, a result from a class, result to identity V. Implies there exists a unique P such that well, what is P? I'll tell you what is P. Right? So P is precisely the identity matrix, but not with respect to the same basis. I'm not going to put B and B, I'm going to put B and B prime. Such that what happens if you look at B with respect to B prime, no, with respect to B, equals the identity matrix. So the point is this, apply, sorry, don't write down that first yet. What happens if you apply identity matrix, basic identity transformations matrix to a vector? You get identity of V vector, but identity of V is just V, and that's exactly this. So that is part one. There is unique matrix P by the class. Part two is, this is very simple. Now, I mean, let's look at the right hand side maybe. Oh, I forgot to say that it's invertible, right? So I should have said here. Oops, my bad. Maybe I'll write it in blue so you can read it. Moreover, P is invertible. How do I know P inverse exists? Moreover, P is invertible. So how do you prove P is invertible? That is the last part, then you can prove part two. This is sort of part A. Part B, why is P invertible? Well, because I can compose with the identity matrix, right? So check that P inverse equals the identity matrix, this time from B dash to B, works. What do I mean by works? I mean that this matrix times this is identity and this matrix times this is identity, and that is obvious by this remark. Using this above remark, check that this is indeed the invertible, is indeed the identity matrix's inverse. Now I come to the proof of two, and now that's obvious, right? If I know the formula for P inverse, I can just start from the right hand side as I wanted to do and calculate. This is P inverse, so is P inverse, so this one, identity B dash B, then T B, B, yes, and then the P, identity B dash. And now you can apply the theorem, the proposition that we just proved. The proposition that we just proved, which was that if you multiply two matrices of linear transformations and the bases are compatible, then that's the same as composing the transformations. So this is really identity composed with T composed with identity. And it's B dash, B dash. But of course, identity composed anything is that thing. So that's why this is true. Finally, 3. 3 says T is invertible if and only if this is invertible. Let's prove both sides. Let's start by supposing T is invertible. This should be a short one. Say T is invertible. But then we know what to do, right? So implies, what does it imply? It implies that T inverse exists and is a linear transformation also from V to V, going the other way. Right? Now what do? I just let P be the matrix of T with respect to B and B dash, and Q be the matrix of T inverse with respect to B dash and B. What can we say about P times Q? So by the same proposition, P times Q is T times T inverse, is identity. Right? Composing two maps gives you identity on V, and the basis is BB. But identity BB is always identity. And similarly, you can do Q times P is identity, is identity transformation, not matrix. Identity B dash, and that is identity. So PQ is identity, QP is identity, therefore these are inverses of each other, and in particular, P indeed is invertible. So Q equals P inverse, in particular, P is invertible. That is the proof that if a transformation is invertible, then its matrix is invertible. How about the other way? If a matrix is invertible, why is its transformation invertible? Oops. This eraser is coming undone. Okay, conversely. Okay, conversely, what do you do? Well, you just directly claim that T is 1 to 1 and on. Say, so T is linear. All you need to prove is T is 1 to 1 and not 2. T and of course that will finish the theorem. Right? So proof. Why is T 1 to 1 and not 2? Yeah. Let's see how much data I put. This today might be a relatively shorter class. Let's see. Okay. So first of all, let's say it's okay, 1 to 1. Right? So suppose T of V equals T of V prime. We want to prove that V and V prime are obviously vectors in V. You want to prove that V equals V prime implies T of let's just do it the simple way. Let's just do it by saying that T of V equals T of V prime. So convert applied matrices. Apply this with respect to B. I want to say TBB prime, right? So let's say TB implies what and the theorem and results from class and a previous result. And what do you get? You get that you start with T VB. On the one hand, that is equal to T BB prime times B prime. Okay. Now, since TV equals TW, therefore this is equal to TB prime B. But again, by applying the previous result, this is T BB prime B prime. So I have this same matrix times this column vector equal this same matrix times this column vector. And I know this matrix is invertible. So I can apply the inverse on both sides. Pre-multiply by this matrix in this fact that it has inverse. So pre-multiply by this to get B prime equals B prime with respect to B. So these are two vectors in the vector space V which have the same coordinates with respect to an ordered basis, which means they are the same linear combination of that ordered basis, which means they are the same vector. So indeed it's 1 to 1. How about onto? So onto says that if I start with the vector V, anything in the vector space, V should be equal to T of something, right? So how do you check what that is? Well, you just literally apply. The coordinates, take the inverse and apply the coordinates. So given, let's call it W. We want to be in V such that TV equals V equals W. You want it to be onto, right? So you want that everything should be the image of some vector. Okay, so how do you get this V? Literally write down WB prime. I'll in fact see what it is, right? So define V via. So you can define V by saying what combination of the basis vectors you want. I think I might want is equal to. Remember that this matrix exists. This matrix is invertible. This should be B prime. This should be B. So take the vector W. Right? I'm given W. So I can convert W into a coordinate vector with f to the n using the basis B. Now I know that T B prime is invertible. So you can multiply with the inverse of this matrix, this vector. This is literally matrix and vector multiplication. We did that. We obtain a vector. Call that B prime, meaning take that combination of the basis elements B prime, not B, but B prime, and call that vector B. The claim is this works. Let's compute what is T of B. Why is it behaving? Okay, fine. Let's say it. Now then TV, let me say with respect to B, is what? It is T BB prime times BB prime. That's by class again. But with BB prime we have a formula for that. This is equal to T BB prime times T BB prime inverse times W B. And now because this matrix is invertible, these inverses of course exist, make sense, and cancel, and so you just get W. So therefore, again, TV is a vector whose coordinates with respect to B, this ordered basis B, equal the coordinates of W with respect to the ordered basis B. And this implies TV equals W. Take that same linear combination of the ordered bases, you get TV on the left and W on the right. And so T is indeed 1 to 1 and onto. This is the onto part. And therefore it is a linear transformation. Therefore it's an isomorphism. So if the matrix of T is invertible, then so is T itself. I don't know if this is ruining my blackboard or not. Okay, so that is that. Am I done with this thing now? Yes. So now we come back to this the final application. As I said at the beginning, I want to tell you about another application of rank-nullity theorem. So that ends the ordered basis part. We might not even see ordered bases again in this course. I mean, like theorems about them, we will use them, of course. Okay, so this is the following. Suppose I know that I have a linear map. Sorry, that's the whole point. Suppose I know I have a linear map from let's say F3 to F3, okay, or from one three-dimensional space to another three-dimensional space. I don't need that space to be F3. Suppose I also know that that map is 1 to 1. Then I claim I already automatically know that the map is onto, and therefore an isomorphism. Okay? I don't need to separately check. If I only know 1 to 1, then I know it's onto. Almost magical, but maybe not, and that's the whole point. The point is, it is not as much magical as trivial once you know the rank-nullity theorem. So let me tell you why this is almost expected in some sense, or why, or at least an analogous statement to this. So suppose this is the following is an obvious statement for finite sets. Okay? Well, let me tell you what it is. So recall, when you talk about bijections, 1 to 1 and onto and so on, suppose I have a set of 3 elements and I take a function to another set of 3 elements. Okay? If this function is 1 to 1, then because these 3 elements have to map to 3 distinct elements there, and there are only 3 elements there, then it is automatically onto. Or if it's onto, then these 3 elements have to map to 3 elements, so they must map to distinct elements. So it's also 1 to 1. So these are all equivalent statements. Recall, if x and y are finite sets, with x equals y, the size of x equals the size of y, then the following let's say and f is a function. Then the following are equivalent. Very simple. 1, f is a bijection. 2, f is 1 to 1. And 3, f is on. Exactly similarly, we have the following theorem for a linear transformation. In exact parallel, if this grammatically makes sense, I have to write all these things again. So maybe I should write them over there. Second. In exact parallel, sorry, second. Okay. In exact parallel, 1 second. So this is going now slowly. Okay, theorem. Not theorem. Let's call it a corollary. As I said, it's literally a special case of the rank-nullity theorem. So, okay. So given B and W, then so say B and W finite dimensional vector spaces over a field F, and the dimensions are equal. That is the point about these sizes being equal. Now, instead of saying it's a map between bases, like these are the, you can think of X and Y as the set of bases of V and W, so that the size is equal of a basis means the dimensions are equal of the vector spaces. And then you have a map taking some basis to some basis. But let's not do that. Let's say given a linear map, given T from V to W linear, the following are equivalent. And you know the same, you know the following, which is T is a bijection, T is 1 to 1, and T is 1 to. Okay? Great. Proof. Okay, the proof is very simple. First of all, if it's a bijection, then it clearly is 1 to 1 and 1 to 2. Clearly, 1 implies 2 and 3. Okay, now, how do I prove 2? So I'm going to prove 2 implies 3. Now, suppose I prove that, suppose I know T is 1 to 1. If I can prove that T is on 2, then that means it implies that it's a bijection, right? Okay, how do I do this? Well, let me write something here. T is 1 to 1 is if and only if the kernel is 0. What is the nullity of a linear transformation? It is the dimension of the kernel. So this is a vector space is 0 if and only if its dimension is 0, right? There is only one 0-dimensional vector space, that is the 0 vector space. So linear transformation is 1 to 1 if and only if the nullity is 0, because if and only if the kernel is 0. And similarly, T is on 2 if and only if the image is the whole space. The dimension, oh god. Let's write down here. Let's call it equals n. I need to give a number to the dimension, right? Like here we had it. I didn't even have it here. That's fine. Okay. So now T is on to if and only if the image is the full space W. If and only, but there's only one full space, one full subspace of W, which is W itself. So if and only the dimension is n. But what is the dimension of the image? It is precisely called the rank. And now this is trivial, right? Because if the nullity is 0 and the total dimension is n, then what does the rank nullity theorem say? The rank is n minus 0. N minus the nullity. And I will leave you to do 3 implies 2 and hence implies 1. So the nullity is equal to n minus 1. That is obvious. This is exactly the same proof. So that's the corollary. Okay, great. So that's that. Now, so if you look at this statement here, and I'm going to now move from another application to a completely different chapter now. But the chapter is very nicely motivated by this and this. If you look at finite sets and you look at linear transform and maps between them, and you look at linear transformations of finite dimensional vector spaces and maps between them, these two seem nicely parallel to each other, right? And that is not a this. That's what I'm going to tell you now is that there is indeed sort of a common structure, which is what people study. And that structure, the idea of studying such a structure, or studying different sets, maps between them that preserve the structure, like linear vector space, and a map preserving linearity, a finiteness, and so there's this idea of a common structure and of maps preserving the structure is what is called category theory. So I'm going to tell you just a very, very quick introduction, sort of a very quick look at it. A very quick look at category theory. And we will see some basic constructions called products and co-products. And we will see those in the context of categories, but basically the idea is to see them for vector spaces. I don't just want to do the direct product and direct sum of vector spaces, which we will, but we also want to talk about dual spaces as well. And we want to talk about tensor products. The whole point is to get to tensor products. And for tensor products, I need to talk about, I believe, quotient spaces. So we will talk about subspaces, we'll talk about quotient spaces, and some things called universal properties. Okay, so that's where we are going. But first, let me start by telling you about what is a category, what is a structure, what is this nice way of encoding structure, and examples include finite sets or sets, and maps between them, vector spaces or finite dimensional vector spaces, and linear maps between them. Yes, that's where we are going. Okay, 1 second, sorry. One second. Maybe I should switch to, no, that's fine. Okay, so that's a definition. Yeah, so the idea is basically there are two kinds of entities. One is objects or things, objects with some structure. So I don't know if the Algebra 1 students who are taking this class have seen categories or not. Maybe in this new syllabus they might not have. And the other is maps between these objects, like set maps or linear maps. And preserve the structure. Okay. Yeah, sorry, it works. Sometimes it complains. Okay, so maybe I should just give you a definition. A category consists of again, so I should point out the remainder of this week's, most of this week's remaining part of lecture, this and the next lecture, will not really be on your syllabus as far as exams go, midterms and finals go. Okay, like I won't ask you what is a category or a midterm. Do something with categories. This is just to sort of give you an idea of important. This is a very convenient dictionary in mathematics to encode things. Then you can talk about the category of vector spaces. You can talk about the category of representations of some group or of some Lie algebra or of some. And you can talk about of some algebra itself of some ring. You can talk about the category of modules over a ring. You can talk about a subcategory of modules over a ring that satisfies some property. So various things you can do. Yeah. So anyway, for now it consists of two things. One is a. So you can talk of the category of all sets. Now, under the current, under the set theory axioms that one works with, called the Zermelo-Fraenkel, I guess, axioms, there is nothing like the set of all sets. That cannot be done. Then you run into like logical contradictions. You might have seen, I guess, who's Bertrand's paradox or something, Bertrand Russell's paradox. Anyway, so does the set of all sets contain itself as a set? Things like that. Anyway, so you can't talk of the set of all sets, but luckily, Zermelo-Fraenkel theory or whatever, the foundations of mathematics as we sort of use them currently allow us to bypass, circumvent that, and say we can talk of a class of objects. Actually, I should have given the class a name, a class or a category of objects. Okay, these are objects. And then for every object, for all objects, X and Y in C. I'm not saying belongs to C because C is not a set. So I'm saying in C is set. Now I have a set of what one calls morphisms, which we denote by mor xy. Of course, morphisms is short or a longer word for morphisms that Algebra 1 students would have seen is homomorphisms. Okay, so those are a special case of morphisms in a category. If you can read my handwriting, that will be a miracle. Okay. Okay. I'm not saying that this set is non-empty. It might be empty, I guess. And then there are satisfying. So 1 and 2 satisfying two things. One is that if you, so for all set X and Y, I can take Y to be equal to X. If I take Y to be equal to X, then necessarily that set of morphisms is non-empty because it has to contain at least one map from X to X. That map is called the identity map. Right? There exists an identity map X belongs to morphisms from X to X for all X in C. And B, the morphisms have to compose. So there exists a composition map, composing map. Composition maps are associated. Basically, composition is associated, meaning composition is well defined, it is defined and associated. Defined meaning what? Meaning what we probably think it does. Sorry, oh, I should say composite, well defined and associated with identity. So I'll just tell you what that means. It means so basically you can guess what it means. Right? This eraser is going with identity, which means i.e. If you look at the morphisms from Y to Z, cross morphisms, i.e. there exist maps. I don't even know what to call them. I.e. there exist, let's call them phi, good, x, y, z, from morphism y cross z to morphism cross morphism x to y, to morphisms from x to z, sending g, comma f to what? Well, you can imagine, right? You take first apply f and then apply g. This is the notation. This is just a symbol. In a category, I have not told you these are actually functions from a set to a set. So they can be whatever they are. I'm just saying that this is how you define like this is the definition of this. This is phi x, y, z of g, comma f. We're just calling it that. But now the point is, it's being written in this language so that so there exist these maps. That is the defined part. What about the associative part? Such that if you take four objects now, morphisms of w, sorry, z comma w, let's call this, I guess, h, and morphisms of y comma z, morphisms of x comma y. Okay. Now you can do the following, right? So let's say this has a h is here, g is here, and f is here. You can do the following. First, you can pair this, and you get to so you get from h comma g comma f. First, you can pair these two. You get h compose g comma f, and then you can pair these two. This is in morphism of z comma, sorry, in morphism of y comma w and an x comma y. And then you can pair these to get w from w to x. Sorry, x to w. And so you get h compose g, compose f. On the other hand, I could have paired these two first. I would have got h comma g compose f. And this would be from, again, this is zw, and this is xz. And now from here I can pair these two, and I get again to x. So I get h compose g compose. Okay? And the claim is that the axiom on the category is that these are equal. And these, of course, belongs to morphism of x to w. X to y, y to z is equal to w. Right? That's what we are saying. That you can compose in either way and they're equal. This is the defined part, this is the associative part, and the identity part is obvious. It is that if you have a, let's say, f belongs to morphisms of x, y, then you can first apply f, and then you can compose. So now you're in y, now you can compose with the identity morphism in y. This is still from x to y. Okay? Then that is equal to f. Similarly, you could have first applied the identity from x to x and then compose with f from x to y, and you would still get it. So that is what a category is. Fine, that's what it is. So these are the axioms of a category. And you see, therefore, now so I'm going to give you examples. So for example, the class of sets and maps between them satisfy is indeed this. By the way, I should point out that of course these maps make sense whenever the particular sets are non-empty. So at least when these two sets are non-empty, then this map makes sense. So you have to keep that caveat in mind. So let's do examples of categories. But basically, you name it and it's an example. The category of groups, the category of rings, the category of vector spaces, the category of sets, the category of finite sets. Right? So all these things are fine. Great. Now let's go back to examples. What I want to do, I want to do these in parallel. So, I'll do sets here and I'll do vector spaces there. Examples. So, category of sets. Sets are the objects and functions or maps. are the morphisms. And then again, you see, of course, so yes, from every, so then you can talk of any two sets, non-empty sets, let's say. Of course, if the set is empty, then you would have the empty set of morphisms. But if X and Y are non-empty, then you would have a non-empty set of maps, and indeed non-empty. And now there exists an identity map function from X to X. Yes. Composing is well defined and associated. Of course, yes. And that's the whole point of composing function. It is well defined and associated. Okay. So okay. So fine. And now here there is one set, but now just like we talk about vector subspace, it is a subset that's a vector space. Oh, yes. Sorry, 1 second. It is a vector space. It is a subset that's a vector space. It could be a vector space in its own right, but that is not a subspace. It's a vector space using the same operations. So the same thing happens here. You can talk of, do I want to mention anything more about this? So maybe I should just say that just more precisely, morphisms of x comma y is the set of functions from x to y. Okay, and now this contains, let's call this 1 prime, a subcategory that we call maybe C fine, fin, as finite sets, and then the same functions as the maps. Okay, similarly, I can talk about, now I talk about the example we care about. The category is vec F, which is the set of, sorry, not finite dimensional, vector spaces, F vector spaces. But now the point is this, of course I can define the morphisms to be arbitrary, arbitrary functions between vector spaces. But that's not very useful. And how are we using the fact that the object is a vector space if we are taking arbitrary maps between them? The correct thing to do is to look at maps between vector spaces which are also linear, or in other words, which respect the structure, the linearity structure encoded into a vector space. So that's what we do. And then more xy equals lin xy. And then indeed every such set is non-empty because at least the 0 is a vector space. There is no origin. No vector space is the empty set. The 0-dimensional vector space is the single set 0. So indeed there are linear maps. For example, from every vector space to 0, the 0 map. From 0 to any vector space, also the 0 map. So indeed this is never equal to empty set. This is always non-empty. Okay, yeah, that's vector space. And similarly to prime, I can look at the subcategory of finite dimensional vector spaces, which is again finite dimensional F vector spaces. And then the morphisms are linear maps. But you can do this for other things as well. So remember in the field, we talked about a field is a set which is a plus, minus, 1, 0, and then times divided by and 1. And so if I forget the times divided by and 1 and just focus on the plus, minus, and 0, then that structure is called a group. It's a group under addition. You call it class. Right? And in fact, it's what one calls a commutative group, an abelian group, because addition is commutative. You can also have non-abelian groups, of course, like groups of transformations or structure permutations. Anyway, so the point is, those also form a category. I can talk of the category of groups and maps between them, which I'll just say because you guys in those among you who are in Algebra 1, the math majors and so on, in PhD students, you would have seen this, right? So let me just tell you about groups. And this is why I said that what we are discussing today, like right now, is category theory. This is not going to be on your syllabus. Because I mean, the rest of you might not have seen a group or something like that. Well, now you have. Every vector space is a group. and every field is a group. But I won't define a group, but basically I'll just say. Maybe I'll use a group and 3. The category is the set of all abelian groups. Abelian or commutative groups. So this is going as well. Together with group homomorphism. So this one works. Wait. Sorry. I should really write this down correctly. Homomorphisms. So this morphism is really homomorphism for the groups. So now what is, again, groups are by definition always non-empty. You never find an empty set that can be a group. Therefore, what it means is that we have a so let me remind you, so let me tell you. A group is basically the same thing as the first part of the definition of a field. A group is a G, an abelian group. I'll just do abelian groups anyway. This is not a group theory class. Is G, plus, 0, minus, where G is a set, 0 belongs to G, plus goes from G cross G to G, is, let's say, is commutative, associative, and associative. And I have already defined what these mean on the first day of class in the field axiom, so I will not do that again. And minus is the inverse. So, and then G plus 0 equals G for all G, and minus is minus G plus G equals 0. So minus goes from V to V, minus goes from G to G. This is called an abelian group. And now you can again talk of groups, the set of all abelian groups, or the class of all abelian groups, or the category of all abelian groups. What are the maps between them? Well, now the map is literally exactly this. The map is something that respects the quantification. So let's say phi from G to H is a group homomorphism. I'll just say group hom. If phi of G plus G prime equals phi of G plus phi of G prime for all G and G prime. From which you can check what happens if you have phi of 0 plus 0. It is 0 plus 0 is 0. So phi of 0 equals phi of 0 plus phi of 0. Now I can add the negative of phi of 0 to both sides to get that phi of 0 equals 0. So phi takes the 0 element in G to the 0 element in H just using this addition axiom. I don't need to extra ask for it. It gets it for free. And now since phi of 0 is 0, look at phi of G plus minus G. You get phi of 0, which is 0. On the other hand, that is equal to phi of G plus phi of minus G. So phi of G plus phi of minus G equals 0. So phi of minus G must be the negative of phi of G. So I don't need to impose any axioms about the 0 or the inverse being respected by a homomorphism. I get that for free as long as the homomorphism respects the addition. So you see there is one binary operation called the addition here, and a group homomorphism or a morphism of groups or a morphism of groups right, is one that simply respects the addition, and that implies that it respects the other two operations as well. It respects 0, it respects minus. Okay? And whether the set of homomorphisms is these are denoted by the set of these is hom GH. So you see this language keeps changing from setting to setting. For sets, it was called function xy. For vector spaces, it was called linear maps xy. For groups, it's called Hom gh. But overall, the common language is that of morphisms from x to y. But the idea is exactly the same in all of these three different settings. So this is a vector, this is 3. And similarly, I can ask for 3 prime, which is finite groups and their morphisms, 3 prime. C equals finite groups, finite abelian groups. And then the homomorphisms, group homs. Okay, so again, in all these 3 settings, whether it is sets and things between them, or vector spaces and things between them, or groups and maps between them, as long as your maps respect the structure, you have the same axioms being satisfied along all of them. For example, the set of group maps is in, first of all, this is always non-empty because every element from G can be sent to 0. That is a group map. You can check it satisfies this. Phi of anything is 0. So 0 equals 0 plus 0 in H. Sure, that's true. Or yeah, so for example, this is always non-empty. And now not only that, you can compose group maps. If you take phi compose phi prime, then it behaves very well. The composite of 2 group maps is a group map, just like the composite of 2 linear maps is a linear map, which we verified. S compose T of C times V plus V prime, we verified that. The exact same thing happens here. Okay, so no changes. And then the next one is what else was there? There should be an identity map from G to G. Well, yes, the identity map of G plus G prime is identity G plus identity G. That's obvious. So identity is a morphism. And composing maps being composites of functions, of course, associative respects the identity and is defined. So everything works. So the key point is that the sets, this category of sets, all of these guys, whether it is abelian groups or these or that, all of them sit inside the sets. And the morphisms are not the same set of morphisms, but they are a subset of morphisms for each one. Each of them is a map of sets from G to H, a map of sets from X to Y, and therefore they are part of this data. And that is why the composition axiom of category theory is respected, because it works here, therefore it works in both of them. And but strictly speaking, you should not. So therefore, the category 1 contains the category 3 of groups, contains the category 2 of vector spaces. The more structure you add, the smaller the category becomes. And similarly, of course, 1 prime, these are all the finite parts. Okay, 1 prime doesn't contain this. 1 prime contains 3 prime, finite sets, finite groups. But it does not contain finite dimensional vector spaces unless the field is finite. Okay, so there are all these, you have all these kinds of nice inclusions of categories and so on and so forth. But again, this was just to tell you that there is a language in which to describe objects possessing structure and maps between these objects that respect this structure, and all of these things are very related. And the point is now what we define, we can define things like a direct sum, a direct product, and so on, which we will. But but we will not. But one checks that in fact these are these can be defined for a product of sets, product of groups, product of vector spaces. And let us start with the notion of a product. Sorry, I need to define an isomorphism and then we'll start the product. The point is, you know how to take products of sets. Your x1, x2, x3, you can take x1 cross x2 cross x3. And what is a nice thing, why is it called a product? Because if x1 has 5 elements, and x2 has 2 elements, and x3 has 2 elements, and x1 cross x2 cross x3 has 5 times 2 times 3 elements. So this is the product of the sizes. Hence it's called a product, right? So similarly, you can take products of sets, you can take products of vector spaces or products of groups. And it is the same thing. The object is such that the operations behave nicely. And there is a way to formalize that, just like we formalize the identity and the composition operations in the definition of category. There is a similar definition of a product, a categorical definition of a product, which specializes to exactly the Cartesian products of sets and the direct product of vector spaces and so on. So let us go into that. First, as I said, I need to define an isomorphism. When is a morphism called an isomorphism? And remember, we had isomorphisms, right? So we had isomorphisms of vector spaces. Well, similarly, you can talk about morphism of groups being an isomorphism, or a morphism of sets being an isomorphism, and that's literally just saying it's a morphism, which is a bijection. Because for sets, it's a bijection. All of these are sitting inside the category of sets. Therefore, for them as well, it's a bijection. But that's not the categorical definition of isomorphism. So let me define that. Let us use maybe a definition. Oh, wow, yes. Okay, I will go to Cartesian product next time, but maybe this is a good time to start. So let me just define an isomorphism. And isomorphism, sorry, a morphism is an isomorphism? Yeah. So, a morphism, let's say F belongs to mod xy in a category C, is an isomorphism. Yeah. If there exists a map G from y to x, I guess that must be the case, yes. Such that, so the point is, I don't know anything. I can't use anything in the general category, right? I've been given very few axioms to play with. But the point is, that's the point, that you have to define everything in those basic terms with no extra structure like you have a set or you have a group or you have a vector space. No, you can't use any of that. And yet you have to define an isomorphism. So this is the way you define it. You can't say it's a bijection because I'm not telling you that these are sets. These could be completely different things. They need not be sets. Although in practice, everything we do with categories most likely refers to sets, except for people who work in mathematical logic or category theory. But nevertheless, if there is a G such that if you take F first from X to Y and then G from Y to X, then this is the map from X to X, and of course this had better be equal to the one map that I know exists. And similarly, F compose G is identity. That's a morphism, and check for yourselves. And the point is that these both have to be in the set of morphisms. So for vector spaces, they don't just get to be any set maps, they have to be linear maps. Check that isomorphisms, in this sense, in this definition, agree with or are precisely. So you at least know two categories, the category of sets and the category of vector spaces. In the category of sets, these are precisely bijections. And linear isomorphisms. I will leave this to you guys to check. Okay, so I think that's it for today. We will continue with direct products and direct and co-products and so on next time. Okay.